Hello everybody. In this video, we're going to consider some problems from physics. So we're going to take a look at how to calculate work or the energy required to move objects. Now these examples are going to further illustrate how this technique of discretizing a problem into little small pieces and then summing them up and using the fundamental theorem of calculus to obtain an integral answer. So before we begin with some examples, let's recall the common units that we use in the metric system. Most of our discussion will be using metric units. So in particular, in the metric system, when we talk about distance, that's usually going to be in meters or kilometers. So you should all know that. Time, same as in the imperial or English system, seconds, hours, minutes, okay? Now, in the metric system, mass is measured in kilograms or grams, usually. Velocity, meters per second, kilometers per hour. Acceleration is going to be meters per second, or meters per second squared. Okay, so that's the common unit for acceleration that we'll be using, meters per second. So what that tells you is the rate at which your velocity is changing. You see, meters per second is velocity. This is a velocity. So it tells you the rate at which your velocity is changing each second. That's what an acceleration is. Force is measured as mass times acceleration. So the force tells you if you have a particular mass of so many kilograms and you accelerate it at a certain rate, if you multiply those two together, that gives you the force. Okay? So the units associated with that are kilograms times meters per second squared. And that's also known as a Newton. Okay? So that's the standard unit for force in the metric system. The amount of work done by moving an object is the distance you move it times the force required to move that object, as long as the force is constant. Okay? Now we'll talk about what happens when that force is not constant. Okay? Now the units associated with this are kilogram meters squared per second squared. Notice if we take the unit of force up here, which is kilogram times meters per second squared, and multiply that by a distance, which is meters again, we get kilogram meters squared per second squared. So that's a unit of work or energy. And the units associated with that are normally referred to as joules, or just abbreviated J, or Newton meters, NM. So those are the units associated with work in the metric system. Power we're not really going to be dealing with so much in this lesson. Power is normally referred to as a watt. That's the normal unit you deal with for power. And that is the rate of work. So that has units of a joule per second. Okay. Now one thing to note with the metric system is how we measure forces near the surface of the Earth. So this is an important thing to take note of. Near the surface of the Earth, you have probably seen or heard this in another course somewhere. Near the surface of the Earth, acceleration due to gravity is 9.81 meters per second squared. Okay, so at the surface of the Earth, if you, near the surface, if you drop an object, it will accelerate downward at the rate of 9.81 meters per second, or meters per second squared. Okay? So what that means is if you, near the surface of the Earth, if you drop an object, after 1 second, it will be traveling 9.8 meters per second. That will be its velocity after 1 second. Okay, after 2 seconds, you multiply this by 2. So after 2 seconds, it will be traveling 2 times 9.81 meters per second. Then after 3 seconds, it will be traveling 3 times 9.81 meters per second. Okay, so that's what acceleration near the surface of the Earth means. If you drop an object, each second its velocity increases by 9.81 meters per second. Okay, now in the English system, it is 32 feet per second squared in the English system, or the imperial system. 32 feet per second squared. Okay, so what that means is if you drop an object near the surface of the Earth, in 1 second it will be traveling 32 feet per second downward. In 2 seconds it will be traveling 2 times 32, or 64 feet per second, and so on. Okay, now let's take note of this. Near the surface of the Earth, acceleration is 9.81 meters per second squared downward. So if you are to, if you take a 1 kilogram mass and near the surface of the Earth, you hold it in your hand, say you have a 1 kilogram mass, the Earth wants to pull it downward, wants to accelerate it downward at 9.81 meters per second squared. For you to keep it from falling, you have to push upward with a counteracting force. The force that you have to push upward with in order to keep it from falling is going to be, from Newton's law of motion, force equals mass times acceleration. So to keep this 1 kilogram mass from falling downward, you would have to exert a force upward of 1 kilogram times acceleration near the surface of the Earth, which is 9.81 meters per second squared. Okay, and the 1 has units of kilograms there. So to keep it from falling and to hold it stationary near the surface of the Earth, you would have to exert a force of 9.81 newtons pushing upward. Okay, or approximately 10 newtons of force. So you take a 1 kilogram mass, you hold it stationary in your hand, you would have to exert a force of about 10 newtons to keep it from falling downward. Okay. Now down here we have units in the imperial system, or the English system. We won't be using these too often, but we have them listed here for you to consider. Distance is usually in feet or miles. Time is also seconds, minutes, hours. Mass in the English system is, you've probably never heard of this before, it's called a slug. Okay, you might have thought maybe mass is pounds. No, that's actually a force in the imperial or English system. So a force in the English system is actually measured or has units of pounds associated with it. Okay. Velocity is feet per second normally, or miles per hour oftentimes. Acceleration, feet per second, or feet per second squared. Okay. Work is distance times force, and that has units of feet times pounds, or foot-pounds. Okay. And acceleration near the surface of the Earth is 32 feet per second squared downward. Okay. Now let me mention just a little bit more about the difference between mass and force in the imperial or English system. If you, for example, say you weigh 180 pounds, that's the abbreviation for pounds there. So you weigh 180 pounds. What that is actually stating is that at the surface of the Earth, if you're standing, you know, on the ground, That's a statement about how much force your feet are exerting on the ground. That's actually a measurement of force in the English system, okay? Whereas if in the metric system I made the statement that I weigh, say, 80 kilograms, that would be a statement about my mass. Okay, so you could think of that as a statement sort of like how many atoms and types of atoms my body is comprised of. Okay, so they're saying two different things. Now, if in the English system, if you wanted to calculate the mass of an object that weighs 180 pounds at the surface of the Earth, you have to remember that force equals mass times acceleration. So in the English system, this is a statement about force. And in the English system, acceleration at the surface of the Earth is 32. So your mass would actually be 180 divided by 32. And the units associated with that is called a slug. You don't normally deal with that very often in the English system, but that's how you calculate mass. Okay, we're not going to have to worry about that in our lecture here, but just for some information there. Now keep in mind, here are some conversions that we have down here. So for example, 1 meter is about 3.28 feet. 1 newton is about 0.2248 pounds. 1 joule is about 0.737 foot-pounds. So those are conversions for some units between the metric and imperial system. Now here's an incorrect conversion that people oftentimes use. You'll see many people state that 1 kilogram is approximately 2.2 pounds. You know, that's really not correct to state this, because these are two different units. Okay, a kilogram is a statement about mass, whereas a pound is a statement about force. So now near the surface of the Earth, you know, it's sort of okay to think of this conversion equation at the surface of the Earth. But in reality, what we should say is, if you realize that a 1 kilogram mass at the surface of the Earth, if we use force equals mass times acceleration, you know, mg, mass times the gravitational acceleration near the surface of the Earth, for a 1 kilogram mass, the force exerted on the surface of the Earth, if it's just sitting there, is going to be 1 times 9.81. And so that's 9.81 newtons. Okay, so really you should say 9.81 newtons is approximately 2.2046 pounds. That's a correct conversion. But people will oftentimes state this. But that's, you know, it's sort of okay to think about that, but it's really only valid at the surface of the Earth. Of course, we already have talked about Newton's law of motion. Force equals mass times acceleration. Now with all of this covered, let's take a look at some definitions for work and some examples. Now here's our definition for work, which we've already seen previously. If you have a constant force F that is applied to move an object through a distance d, then the amount of work performed on that object is simply force times distance. Now the units in the metric system associated with that is normally joules. Now what that's going to be is Newton meters, remember, because force in the metric system is going to have units of newtons, and distance is often going to be measured in meters, and so the units of work are going to be Newton time meters, and that's also called a joule in the metric system. Now in the English system or imperial system, work is still force times distance, but the units are a little different. In the English system, force has units of pounds, And distance is oftentimes measured in feet, so usually in the imperial system, work is going to have units of feet times pounds or foot-pounds. Now let's note something important about this definition. Suppose we have an object like a box, and it's sitting on the floor, and say it's located at position A, and we push on this box with a constant force to overcome the friction between the box and the floor. And we push the box until it is at position B. Now let's let X represent the location of the box. So say the box, for example, is sitting here after we push a little bit, and say that's at position X. Now the force we push on this box with, call it F, that's going to be, in this picture, relatively constant. So F of X is going to be some constant number. Now we move it through a distance B minus A, so the work is going to be force times distance, and that is F times B minus A. All right. Now if we graph the force function, this F of X, it's constant, right? Suppose our x-axis here represents the location of the box, and we graph our force function. It's constant in this case. Then if I calculate F times B minus A, well, B minus A is this distance, the width of this rectangle. F is the height. And so if we evaluate F times B minus A, that gives us the area underneath the graph of our force curve. Okay, so that's a very important concept to understand, because, as we'll see later on, suppose this force varies. Suppose the force varies as we move the box across the floor. Suppose at first the box, it's rather difficult to push, and then maybe we hit a slick spot in the floor and it's a little bit less difficult to push, and then maybe it hits a spot that's a little bit more difficult to push through. So in other words, suppose our force function is variable. Maybe it would look like that. Well then, what would the work be? What does it seem like the work should be? Well, it seems reasonable that the work should still be the area underneath your force curve. And that's going to be represented by the definite integral from A to B of F of X dx. And that's exactly what we'll see in a theorem that we're going to look at in a moment. Before we look at that theorem, let's take a look at this example. So in this problem, suppose we have a barbell that has a mass of 5 kilograms. Now suppose it's sitting on the floor of the gym that we're at, so we have a barbell here, 5 kilograms. And we pick it up and we lift it a distance of 2 meters. So now our barbell is up here. How much work was performed in lifting this barbell, and how much potential energy does the barbell have once it's up here? Well, work equals force times distance. Now the amount of force it takes to lift this barbell, well, near the surface of the earth, force equals mass times acceleration. G is our gravitational acceleration near the surface of the earth. So the amount of force it takes to lift the barbell is going to be 5 times 9.8, or 9.81 if you want to be a little more precise. And that's going to have units of newtons. Then the distance we lift it is, of course, 2 meters upward. And so the total work is going to be 5 times 9.81 or just 9.8, times 2. So this is our force, and this is our distance. And when we evaluate that, of course, we get 98, and that's going to have units of Newton meters or joules. There we go. Now that also represents how much potential energy this barbell has as it's hovering here, as you're holding it. Okay, you're holding it. So as you're holding it here, that represents how much potential energy this barbell has. So if you were to drop it from this height, of course it would fall down, it would smash against the floor, it would create a lot of sound, it would shake the floor a little bit, maybe it would crack a tile. It would also actually heat up the floor just a little bit where it came in contact with the floor. So all of that energy, that potential energy, 98 joules, if you dropped it, would be expelled to the surroundings by sound waves. It would take some energy to crack the tile, to split it apart. The floor and barbell would actually be heated up just a little bit when they would slam together. So that's where all that energy would go if you were to release it, and it would drop. Now let's take a look at this theorem. This theorem tells us how to calculate work if our force function is no longer constant, that is, if it varies with respect to the position of the object. So suppose an object is located at position A initially, as measured along a straight line from some starting location. If we let x represent the position of the object, and a variable force f of x is applied to the object to move it along a straight line to position B, then the total work performed on the object is given by the definite integral from A to B of your force function. Now this shouldn't be shocking because, as we saw previously, if we had a constant force, and we moved an object from location A to location B, then the work was merely the area of this rectangle, which is also the area underneath the graph of our force curve. So it doesn't, so it's not shocking then that if this curve actually varies as we're moving the object, so if that curve varies a little bit like this, say, as we move the object, then the work is still going to be the area underneath our force curve. So it makes sense. Let's take a look at the proof. So here we have the proof of this theorem. So what we're going to do is we have an object moves from position A to position B. So we're going to take the interval AB and we're going to break it into little tiny subintervals like we have pictured down here. Okay, so the object is located at position A initially. We push on it with a variable force. It ends at position B. We take this interval, we cut it into small subintervals like this. Okay. Now each of those subintervals is of width delta x, which is b minus a divided by the number of subintervals we have, n. Now take note in the figure below, on each subinterval the force function f of x is approximately constant. Okay, so if you look on this first little subinterval right here, you see how your blue force curve is pretty much constant. It's pretty much straight like that. So that means that the amount of work that it takes to move the object from here to here is going to be just approximately f of xi times delta x, where this xi, just pick some point in here, call it xi right there. Okay, f of xi is going to be this height, the width is delta x, And so when you calculate this, that will give you the area of that rectangle right there. Okay? So that comes from our definition, work equals force times distance, where the force is constant. On this interval, the force is approximately constant, so we can just calculate it like this. Then all we have to do is sum all of these values as the I goes through each subinterval. Okay? So what we have down here then is that our total work is going to be the limit as n goes to infinity of this summation. Now once again, what this summation represents, each of the values inside the summation, that's the area of all of these little rectangles right here. Okay, so, and then you sum all of them up. Now if we take the limit as n goes to infinity, you see these little rectangles would get smaller and smaller and smaller and fill in the area underneath your force curve. And what you end up with in the limit, using the fundamental theorem of calculus, of course you've seen before that this, when you have a limit outside a sum, this turns into an integral from a to b of f of x dx. And there you go. That's how we calculate the work for a variable force. We simply integrate f of x over the position x from a to b. All right, let's take a look at a few examples. Now let's take a look at this example. So here we have a person standing on a 10-meter high platform, and they wind in a chain that extends down to the base of the platform. Now assume the chain has a mass of 1.2 kilograms per meter. So that's the mass density of this chain. Each meter of the chain has a mass of 1.2 kilograms. Let's find the amount of work it takes to wind in the chain. All right, so down here we have a diagram of what's going on. So you see we have a 10-meter high platform right here. This is our platform. We have a winch here that is winding in the chain, or a person with a crank, some type of crank mechanism with a pulley that is winding in the chain. This is the chain that extends down to the ground. And in this picture, suppose that we have already wound in a little bit of chain, say that distance is x. All right, now what we need to do is calculate the amount of force it takes for us to pull upward on the chain that is hanging down here. Okay, so we wind in the chain. Each time we wind in a little bit more, this force function is going to change a little bit. All right, well, if we've wound in x meters of the chain, then that means that 10 minus x meters of chain is hanging down. Okay, so that's how much chain is hanging down. That's in meters. So then the amount of force required to lift the chain that we have hanging here, well, that's going to be force equals mass times acceleration. Now, near the surface of the Earth, the acceleration is 9.8. Now the mass, what is the mass of the chain that is hanging down here? Well, the length of this chain is 10 minus x. Okay. And the mass density of the chain is 1.2 kilograms per meter. So if we multiply this by 1.2, that'll tell us the mass of the chain that's hanging down. So the mass of the chain hanging down, that m right there, is going to be 10 minus x times 1.2. Okay, you see, if you're standing up here, think of, you're trying to pull this chain upward, and the mass is 10 minus x times 1.2, and then you multiply by the gravitational acceleration near the surface of the Earth. That tells you how much force you have to apply. So down here we have that force function. So you see this is a function of x. Okay, now we have to figure out what we need to do with this function. Well, from the theorem we saw previously, we need to integrate it. But what do we integrate it from? Well, if you think here, this x, when the chain is all the way on the ground, x is equal to 0. All right, so that's when x is 0. Then when you've wound the chain all the way in, x is going to equal 10. Okay, so then the total amount of work is simply going to be the integral of your force function from 0 to 10. And our force function is given by this right here, and so that is going to be and there we go. That's all you have to evaluate. Now that's fairly easy to evaluate. You can do that by hand or with a calculator. And what you'll get is this. So you see the work is the integral from 0 to 10 of our force function right here. Okay. 9.8 times 1.2, that's going to be 11.76 times, and then if the antiderivative of 10 minus x, that's going to be negative 10 minus x, the quantity squared over 2. Okay, see if I differentiate this. If I were to differentiate this, I get 10 minus x. Put 10 in for x, 0 in for x, and subtract those two values, you will get 588 joules. And there you go. That's how you do that problem. So once again, we had to come up with our force function. And the force function is a function of x, where x represents how much chain has been wound up. And then we just had to integrate it. Okay, let's take a look at this example here. This is a slight variation of this problem. So with this problem, we want to redo the previous example. So same as we had before, we have a 10-meter high platform with a chain, mass density 1.2 kilograms per meter, hanging all the way down to the ground. But now we have a 20 kilogram mass attached to the end of the chain. Right here we have a 20 kilogram mass. Okay, so now we have to once again figure out what is the force function going to be as we lift this chain upward. Okay, well, suppose we already have lifted the chain a distance x. Okay, so then our force function is going to be, well, we have to calculate the amount of force required to lift the chain. Okay, ignore the weight on the end of it for now. Just the chain itself, we already saw that the amount of force is going to be 10 minus x times 1.2. Okay, so this is the mass of the chain hanging down times the acceleration near the surface of the Earth. Okay, so that's the force of just the chain. But now we have to add on to it the force due to gravity pulling downward due to the 20 kilogram mass. So to lift this 20 kilogram mass upward requires a force of 20, that's the mass, times gravitational acceleration near the surface of the Earth again, 9.8. And there we go, there's our force function, and of course we could factor out a 9.8 and simplify this as and there we go. Okay, so there is our force function, and that's what we have down here. Okay, so then the work is simply going to be the integral of this force function as x goes from 0 all the way up to 10. Okay, so, and that's what we have down here. Let's just scroll downward. Okay, so you see right here we have the work. We factor out the 9.8 away from our force function, right? Here's our force function. In fact, we can factor the 9.8 in front of the integral. Integrate from 0 to 10 of what's remaining, 1.2 times 10 minus x plus 20 dx. Okay, so that is going to be, the antiderivative of that is right here. Remember, antiderivative of a constant, 20, that's 20 times x. This is just a constant. The antiderivative of this term right here is negative 10 minus x squared over 2, right there. And then we just have to evaluate that from 0 to 10. So you put 10 in here for x, 0 in for x, and subtract the 2, and you will get 2,548 joules. And you'll also notice that if you think back to our previous problem, we had calculated 588 joules just to wind in the chain, right? Now, if we have a 20 kilogram mass hanging on the bottom of the chain, then the amount of force required just for the mass, just to lift this mass upward, well, we want to lift this mass a distance of 10 meters upward, okay? So the force to lift that mass is 20 times 9.8. And so then the work is going to be, now that's a constant, so we can just go, work is going to be 20 times 9.8 times 10, right? And that gives us 1960. And then if we take this number and just add it to the 588 for the amount of work required to wind in the chain, yeah, we get 2,548. So just notice that this is 588 plus 1960, and that makes sense. This is the amount of work required to wind in just the chain. This is the amount of work required to lift the 20 kilogram mass 10 meters upward. And there you go. So we could have done it like that also. Now let's take a look at another type of work problem, and these are called spring problems. Now let's first of all take a look at a law that we have here, and this is called Hooke's law. Now Hooke's law makes a statement that the amount of force required to stretch or compress a spring, x units from its natural length, is given by this equation. Force equals k times x, where k is a constant that's dependent on the spring itself, you know, what the material is made of, how thick the spring is, how many windings it has, and that's called the spring constant. So k is a constant, and x is the distance that you stretch the spring from its natural length. So for example, if you consider this diagram down here, so right here we have a spring, and we have a little mass connected to the end of it. Now right here the spring is at its natural length. So notice the x is equal to 0 in this first picture here. Now if you take this spring and you stretch it, down here we have it stretch a distance x, then the amount of force that the spring will pull back in this direction is proportional to the distance that you stretched it. That's what we're saying here. And once again, that k will depend on the spring, and it can be easily determined experimentally. Now let's note a few things here. First of all, This equation is really only valid for x in a relatively small range around the spring's natural length. Of course, if you were to stretch this spring way out here, well, eventually the spring would start to bend and eventually it would break. So this equation is only valid for x in a certain range around the spring's natural length. Also, the spring constant K has units of force divided by distance, which in the metric system would be usually Newton meters, or in the English system, pounds per foot. And that comes from the fact that if we look at this equation up here, you see we're saying force, so that has units of newtons on this side of the equation. And we're saying that the force is equal to K times x. Now x has units of meters. So if we take the x and divide it to the other side, you see we get that K equals force divided by a distance x. And so the K has units of newtons per meter. And if you're in the imperial or English system, the force up here would have units of pounds, and x would usually have units of feet. So K would have units of pounds per foot. Okay, so that makes sense that those are what the units would be. All right. Now let's take a look at an example. So in this problem, we have that it takes a force of 5 newtons to stretch a spring 10 centimeters. Let's find the amount of work required to stretch the spring 15 centimeters from its natural length. All right, now we have to be careful here to use common units. You notice we're given centimeters here as our units of length, so we may want to convert that into meters. Well, in fact, that's what we're going to do in this problem. If we want to have we want to calculate a unit of work, if we want that unit to be in Newton meters or joules, then we have to convert this into meters. What we have then is that from Hooke's law, right? Now we have to figure out that spring constant. That's what this first sentence is going to tell us. So it takes 5 newtons, so if we put 5 in for F, to stretch a spring 10 centimeters. Now 10 centimeters, remember, is 1/10 of a meter. A centimeter, now just over here quickly, 10 centimeters equals 10 times. Now a centimeter is 1/100th of a meter, so we replace that with 1/100th of a meter, and so you see we get 0.1 meters. Okay, so if we put in place of the x here 0.1 or 1/10, then we can solve this equation for K, and we get that K equals 50 newtons per meter. Okay, and that's what we have right down here. All right, now, so we found the K. The rest of the problem wants us to find the amount of work it takes to stretch the spring 15 centimeters from its natural length. So what we need to do is the work is going to be the integral of our force function. Now in this case, the x here is going to vary from 0 to, well, let's see, 15 centimeters is going to be 0.15 meters. Okay, so what we're going to have here is x will go from 0 up to 0.15, and we just put in for the f of x this equation that we just determined. So f of x is 50x, right? And of course, integrating this, we get and there we go. So if you put 0.15 in for x, 0 in for x, and subtract those two values, you will get what we have over here, which is 0.5625 joules. And that is our answer. Okay, so you see, when we did this problem, we had to first figure out what the K was, since that wasn't given to us. And that came from the fact that it took a force of 5 newtons to stretch the spring 1/10 of a meter. Then once we had the K, we had to calculate the amount of work to stretch the spring 15 centimeters from its natural length. So that's just the integral of our force function from 0 to 0.15. Remember to convert the 15 centimeters into meters, and we obtained our answer.